Hello, everyone, and welcome to the 37th Surface Ventures keynote webinar. It'd be great for you to type in the chat, say hi, tell us where you're joining from. Unfortunately today, due to some small technical issues, I will not have the normal camera source that you would see, so it will just be audio from me today. But my name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we are a non-for-profit organization. And our mission is to provide world-class surface and material science education for academia and industry. Today, it is my pleasure to introduce Professor David Noel of Imperial College London. David has been a professor of machine dynamics at Imperial College since October 2017. Before this, he was a university lecturer at Oxford for nearly 30 years. He's the co-author of 2 books on content mechanics and threading fatigue, and has over 200 journal publications and papers in published proceedings. He was involved with the Rolls-Royce UTC in solid mechanics at Oxford from 1990 until 2017, and is now taken over director of the Rolls-Royce UTC in vibration at Imperial College. Many thanks to today's partner, Optimal Instruments. We'll have a short presentation from Gregor Patzer later in the event. We'll also be releasing some poll questions and handouts from them throughout the event. So we'll begin with some poll questions, as we do normally, and then handouts when Gregor is giving his presentation. As we go along, please type your questions into the chat, and they will be marked for the Q&A sessions, which we will do after both presentations. And we're planning for going for around 60 minutes today in total, and we'll be sharing a link for your attendance certificates later in the event. So without further ado, let's welcome David to the stage and begin with our presentation.
Thank you very much, Sam. I hope everybody can hear me okay. And well, I was going to say good afternoon, but I see we've got quite an international kind of audience. So some of you it'll be afternoon, some of you morning, and presumably somewhere it'll be evening. But anyway, good to see you all, and nice to be talking to you. So thank you very much to Thomas and Sam and the Surface Ventures team for asking me to do this talk, and I'm very pleased to be talking to you this afternoon. And as you probably gathered from Sam's introduction, I've had a bit of an interesting career, and I've kind of done a lot of stuff on contact mechanics, and some instances I kind of think of myself as a tribologist, and then other times I'm a solid mechanics person or a structural integrity person, and then more recently I've kind of morphed into a dynamics person, but actually there is a bit of a common thread running through all of this, and actually engineering surfaces and friction and so on have been quite important to me over the course of my career. So that's what I'm talking to you about today. I want to talk a little bit about engineering surfaces, and particularly rough surfaces, and how they add compliance to problems, and why we might be interested in that when we're analysing engineering systems. A little bit of history here. So most of you will be aware of the Greenwood-Williamson paper on rough surfaces, which goes back to 1966. Last time I looked, it had around 3,000 citations, and I think we'd all love a citation record like that. But the reason for bringing it up, well, of course, it's a seminal paper on vibration on rough surfaces, but also I had the pleasure of doing my final year project on rough surfaces way back in 1982, and my supervisor was Jim Greenwood. So that was really nice. And Jim's still with us, you'll be pleased to know, and still a little bit active, and into his 90s now, but I also had the pleasure of seeing him receive the Tribology Gold Medal last year at the IMechE. So that was really nice to see as well. So I've been kind of involved with rough surfaces really, well, you can see, for the last kind of 40 years or so. And why the first question, I suppose, is why do we have interfaces at all in our components and systems? Well, in our systems, really. And in some senses, they're regarded as rather a nuisance. And I think I might talk a little bit about why they're a nuisance. But there are also, of course, very good reasons for having interfaces in complicated systems like that aircraft engine or the electric car there. It's difficult, of course, to make the entire system from a single component. Very few systems are that simple. We have restrictions on the size of components that we can manufacture. We have restrictions on manufacturing particular geometries, which mean that we have to make things in parts. We need to have different materials in different parts of the system. And we need to be able to take the system apart and replace parts and put it back together. And of course, we need to allow, in some cases, relative motion between components. So all those reasons for having interfaces. But if you look at something like that aircraft engine, and I've done a lot with aircraft engines over the years, you'll see that there's thousands of interfaces in that system. And the problem is that they're not easy things to model. So, and it turns out that actually one of the principal remaining uncertainties in our predictive models of complex systems is the behavior of the frictional interfaces there. These frictional interfaces, or these interfaces, do two things. They introduce compliance into the system, so they're more compliant both in the normal and the tangential direction than it would be the case if we made a the component or the two components as one, and also fortunately or fortuitously, the friction introduces some damping at the interfaces, which is helpful from a dynamics point of view. And but the trouble is it's non-linear, so that's a bit of an issue for us. And the ability to predict contact stiffness as a function of surface roughness and material properties and perhaps as load would be a significant step forward in getting some of our uncertainty out of our predictive models of systems. From a solid mechanics point of view, a good joint, if you like, might be one that has zero friction. So if it has zero friction, we don't need to worry about it. It's the only way it can transmit force is by pressure, and so that's great. Or if we have infinite friction, effectively the two components are welded together and they behave as one. But unfortunately, and I spent quite a bit of my time, I suppose, thinking about friction a bit like that. And you'll see in the top right here an experiment that we did at Oxford on the fretting fatigue of dovetail joints in aircraft engines. But unfortunately, from a vibrations perspective, we want to see some damping in our system because we would like our mechanical energy, our vibration energy, turned into heat and dissipated. And in this second case, the worst system that we can possibly have is one with either zero or infinite friction, because neither of those give us any frictional damping. So we've got these competing requirements in terms of if we could perhaps design our interfaces, we find that we're up against competing requirements, whether we look at the system from a solid mechanics point of view or from a dynamics point of view. And of course, in terms of structural integrity, the system behaves as a whole, and both of these issues are important. You'll be familiar with this equation if you go back to your undergraduate studies. Mx double dot plus Cx dot plus Kx equals some periodic force. So this is the fundamental dynamics equation of vibration. And I quite like it because it's got two of my heroes in it, Isaac Newton there and Robert Hooke. So Isaac Newton said force equals rate of change of momentum, or effectively in our case with fixed mass, force equals mass times acceleration. And Robert Hooke said effectively force equals stiffness times extension. And Well, I don't know if you know much about the history, but Isaac Newton was a Cambridge man. I did my undergraduate studies at Cambridge. Robert Hooke was an Oxford man, and indeed was a student at Christ Church, and that was the college where I taught. And they hated each other, and they got into all sorts of spats about who had thought of what first. And in fact, as you can see here, Hooke died before Newton, and partly as a result, there are no contemporary portraits of Hooke. And that one there is a painting which was done much more recently based on descriptions of Hooke that had come down to us. Now, okay, so those are those two terms, and the term in the middle, the CX dot term, is a linear damping term, and that's what we get from viscous damping, linear viscous damping, so in a shock absorber in a car or something like that. And of course, that's fine, but our frictional interfaces are not going to behave in a linear fashion. In fact, they're anything but linear. Now, the normalized amplitude of response of a system depends on the frequency and on the amount of damping. And you'll be familiar with this sort of one-dimensional, one single degree of freedom system here with a mass, a stiffness, and some damping. And what you see as it clearly, as you increase the damping, the magnitude of the resonance comes down, and also the natural frequency changes. And therefore, it's important to know what the damping is doing, what level of damping we have, and what's the effect on system behavior. But as I said, most fortuitous damping is not proportional, and so we need to understand what's going on a bit more carefully. Now, I had a little video for this, but I was asked not to put videos in the slides. But fortunately, I do have the two gin glasses here, so I can actually do the demonstration for you. So this is a standard gin glass, no gin in it, unfortunately. But anyway, this is one that I pinched, you know, from the sideboard. And if I hit it, hope you can hear that, rings very nicely like a bell. This is one that's got a crack in it. You may be able to see the crack, you may not, but I'm going to hit this now. And what you can see is that behaves completely differently. And the main reason it doesn't ring is because there's a significant amount of frictional damping in the system. And sometimes in our systems, we have this kind of fortuitous damping. So you will see on the right-hand side there, that's a turbine disc with some blades inserted in it. And then on its left, you'll see what they call a blisk, which is an integral bladed disc. Very nice because we can make the whole thing as a single component. It's cheaper to manufacture, lighter, and so on. But I think you can imagine that that one is going to ring a bit like our intact gin glass, and therefore we can expect significant vibration problems with that type of component compared to the system bottom right. Frictional hysteresis. What we find is that friction varies even during a simple cycle. So what we've done here is basically some reciprocating tests. So we take two bodies and we simply rub them against each other backwards and forwards in a fretting situation. And what you find is that initially from bottom left, the friction force increases with displacement more or less linearly. And then the contact starts to enter a microslip slip phase where you see the frictional force starting to come to an asymptote. And then we have a full sliding phase where we can more or less say that the friction force is constant in many situations. And that's from there we get the concept of the friction coefficient. And the area within that loop is the energy dissipated. And as wear proceeds, as we get surfaces interacting like this in sliding, we'll get wear. And as wear proceeds, what we find is that the size of that hysteresis loop here characterized by the coefficient of friction, that increases with the number of cycles, and primarily because the real area of contact is increasing significantly, and you can see that bottom right of the slide where we have wear scars at 5, 8, and 30 minutes into a test, and the real contact patch basically ought to be that complete square that you're seeing. In terms of frequency response functions, the contact has two main effects on the vibration behavior. One is that the nonlinear frictional damping reduces the amplitude, and secondly, the presence of the interface makes the assembly significantly less stiff than if it were monolithic geometry, and so we get a change in the natural frequency. And the other thing we find is that the effect depends on the state of the interface. So you can see here that on the right hand side and in the main graph here, that the wear has shifted the natural frequency. It's reduced the amplitude in some cases, but particularly around this 180 hertz peak here, you'll find that there's been a quite significant decrease in the natural frequency. So this is our little 1D friction rig, developed originally by my colleague Christoph Schringshackle and his students. And we use this to collect hysteresis curves under small amplitude sliding. And here again, we see the variation with friction coefficient as the experiment proceeds. So basically, as wear is taking place. The behavior of frictional contacts is very, very complicated, but just to kind of sort of take you through what I hope we're trying to achieve in our research, we start off top left there with our motivation, which is to understand the joints. We do some experiments, reciprocating type experiments often. We take some measurements. We can characterize the surfaces. This one is a sort of toroidal ring on a flat. And you can see how the wear has proceeded. And then we try and do some modeling, and finally we try and validate those models. So that's what I'm hoping to take you through in the rest of the slides. So my involvement with Imperial actually goes back a long way, and we had a joint project with Imperial many years ago. And what we were trying to do was to measure friction and measure compliance effectively on the same surfaces, but with different equipment. So the Oxford equipment on the left is largely very low frequency equipment. It's quasi-static, relatively large contact, large forces, and so on. And we measured displacement by digital image correlation or by a remote LVDT. And on the right is an earlier incarnation of the Imperial rig, and you can see that the contact area is much lower, 1 millimeter squared. Frequency is much higher, so it's a dynamic experiment, much lower sliding distance, and displacement measurement is done by integrating laser Doppler velocity measurements. Now, the results are quite interesting, and particularly I'd like to show you these two graphs on the right. So what we've got on the right is this is one surface with respect to another, and you can see that within the specimen, the vertical displacement under the normal load is approximately linear with position. And then as we go to the other side of the interface, we go into what we would call the fretting pad. And again, we have a pretty linear displacement variation with position. And that's what we would expect if the two surfaces are being squashed together. But we have a big jump in between. And that displacement jump is effectively due to the compliance of this rough contact layer, all these asperities which sit against each other on the surface itself. And bottom right, you can see that not only do we get that jump, but that jump varies with normal load. So that as we apply more and more load, basically the surfaces get closer together, as it were. So in order to bring them down, bring them to by 6 microns relative to each other, we have to apply a very, very high force. And so there's the normal stiffness. We can measure it in that way with digital image correlation, and we can also do a little bit of measurement with ultrasound, and these were some results that Daniel Mulvihill got. And you'll see again, we're getting the same kind of effect where the normal contact stiffness is increasing more or less linearly with contact pressure or with load. We can do the same kind of effect, but under repeated normal loading. So if you like, squashing the two surfaces together and then letting them come apart and then squashing them together and so on. And we find two interesting things. First of all, that the unloading stiffness is higher than the loading stiffness. And that is probably something to do with plasticity. And also that the stiffness increases with each successive loading. And so you'll see those curves getting steeper as we go through first, second, and third cycles of loading. And that's to do with some kind of hardening behavior and perhaps some shakedown of the geometry. We can measure these tangential hysteresis loops, and I showed you some of those before. And when we do that measurements, you'll see top right there a real close-up which has got the pad on one side and the pads on the right, I think here, and the specimen on the left, and the interface between them. And that's the kind of size of image that we look at. Okay, so what we get from the loop is a representative friction coefficient and then a representative stiffness. And this now is a tangential stiffness. What we were talking about before was a stiffness in the normal direction, and we have exactly the same effect in the tangential direction. And here we are. Here's some loops. So this is giving tangential load on the vertical axis against tangential displacement on the horizontal axis. And effectively, you see that in each reversal of load, it starts off linearly, and then we start to get tailing off of the stiffness as the gradient decreases and the contact is coming near to sliding. And we get rather similar effects here. So we find that we get some stiffening with repeated cycling. So if you look on the left of that graph, the stiffness goes up from, if you like, 1 to 3 to 5 to 7. And then what happens is that stiffness decreases down to 0 as we get near to the point of sliding. And then when we reverse the load, it jumps back up again to values rather similar to what we had when we were sliding in the opposite direction. We can even do now, and this is some of Christoph's work and his group's work, we can even do now measurements of tangential and normal stiffness throughout the cycle. So we're doing continuous measurements of what's going on, and what's plotted in the right-hand side in those colors is that we are effectively measuring normal stiffness and seeing how that varies around a fretting loop And there is quite a bit of variation of normal stiffness around a fretting loop, and that's something that we are, if you like, trying to understand a little bit more carefully by looking at those results. So essentially, tangential stiffness varies with tangential load, but it also varies with normal load in much the same way as the normal stiffness varies with normal load. So we've got a very complicated situation here. We've got this extra compliance, if you like, or stiffness, one's the reciprocal of the other, at the interface, and the value depends on both, in the normal case, depends on normal load, and to some extent on where we are in the fretting loop, so a bit on tangential load. And similarly, tangential stiffness varies with both normal and tangential load. Just to show you some rough contact models. So coming back to the Greenwood-Williamson model, the normal stiffness increase with normal load is implicitly actually predicted by Greenwood and Williamson's model, but the paper doesn't explicitly address that question. And for a Gaussian distribution of asperity heights, we find that the variation of stiffness with load isn't quite linear, but it's very, very close. And what we've done over the past is taken the Greenwood-Williamson model and taken the same assumptions, which is a distribution of hemispherical elastic asperities with constant peak radius. The distribution of those heights can either be normal or it can be an exponential, and what that's representing is the tail of the distribution coming into contact, so relatively light loads. And you assume that the behavior of each asperity is independent, i.e. light load. And the results were published around about 10 years ago now by myself, Simon Medina and Daniele Dini. And what you see is that at low loads, the contact stiffness is proportional to normal load. That was what we measured. But at high loads, the stiffness needs to approach that of an equivalent smooth contact. So effectively, we can't, by putting more load on the contact, we can't make it any stiffer than the value implied by the bulk elastic behavior of that geometry. Nice comparison with Simon Medina's numerical model. You see the pictures at the top there. Each of those spots represents an asperity in contact, and you see as we increase the load by a couple of orders of magnitude, we go from maybe 10 contacts, 10 asperities in contact, all the way up to a large number of them. And of course, at that point, our model, shown by the chain, or the dashed line in the graph there, at that point, the model isn't representative because the asperities are no longer acting independently. Of course, in real contacts, this is purely an elastic model. In real contacts, plasticity will be present, but there's quite a bit of evidence that the plastic effects are effectively rather similar. Tangential contact stiffness, well, you can actually assume that the initial stiffness is related to the normal value, and then as the asperities start to slip, the tangential contact stiffness reduces. So as we say, the modeling side also predicts that we should have this behavior. So there you are. That's about what I've got to say to you. I think what would one conclude from this? Firstly, I think rough contact interfaces are more compliant than we tend to assume in our finite element modeling, and therefore we're not going to make accurate predictions of things like natural frequencies of assembled components. Secondly, the measurement of stiffness in real contacts is not straightforward, but it is possible. Easier with normal stiffness than tangential, but both are possible. The simple elastic model predicts a variation of stiffness with normal load. and it's independent, interestingly, of the material elastic constants. And this is consistent with the experimental evidence, and there is also, as we say, evidence for increase in tangential contact stiffness. Repeated normal loading seems to give a stiffer contact on each loading cycle, and this might be expected if the real area of contact was changing. And tangential contact stiffness decreases with tangential load. And I suppose this is the challenge for the next generation of tribologists. There is a lot of work to be done before we can have a fully predictive model. And in particular, it would be great if we could predict the coefficient of friction between two surfaces. In principle, it ought to be predictable because it depends on things that we understand, like elastic and plastic properties of materials and their geometry, and perhaps something to do with surface condition and surface chemistry and so on. But really, we ought to be able to predict it. But the reality is we can't, and that we need to do tests in order to work out what the friction coefficient is. Top right there, again, another one of my heroes, if you like, but Wolfgang Pauli, very well-known physicist, said, God created the solids, but surfaces are the work of the devil. And I think this is a very apt quotation, because it reminds us that dealing with solid mechanics is easy, really. That the mechanics of materials themselves is relatively easy compared to the mechanics of the surfaces where our components interact. And just to finish off with a few acknowledgements, lots of people have contributed to the work that I've shown you: David Hills, Daniela Dini, Daniel Mulvihill, Simon Medina, and more recently Alfredo Fantetti and Tong Wei. And the funding has been from a number of people, but principally EPSRC, Innovate UK, and in conjunction with Innovate UK, Rolls-Royce, through the UTCs, both in solid mechanics at Oxford and in vibration at Imperial. So that's it from me. So I think we're going to hand over to Gregor now, and then we'll take questions at the end of Gregor's presentation. So thank you very much.
Absolutely. Thanks very much, David. Very interesting talk. And yeah, please, everyone in the audience, do have a think about, some questions to ask at the end of this, as well as, as applied to what Gregor is about to present, and yeah, David's talk. Okay. So Gregor, would you like to set up the slide share, please? No, I'll stay on stage just to make sure that we can all see that. Okay.
Yes, do you see the slides?
Yeah, I think we just need to have this. There we go. That's it. Full screen now. Fantastic. Take it away.
Great. Thank you. Thank you, David, for this very interesting presentation. I learned a lot. And today I would like to first shortly to introduce myself, Gregor Patzer, General Manager at Optimal Instruments. We are based in Munich, Germany, and our target is to develop. For more than 50 years, we've been developing practically relevant test scenarios for tribological challenges that enables you to gain as much knowledge as possible already in the lab scale. And this is our main topic. We develop test scenarios. Of course, we do develop our own test rigs, tribometers, that we always focus on practical applications. And this is what I want to show you with a few slides today. So why we do it? It's quite obvious. By doing lab scale test, you have a shorter test duration than in the field or on a rig test. You have lower expenses, very flexible parameters, and a good practical relevance if you develop the right testing methodology. And on the other hand side, you have a very good and quick data handover for further simulating. So I will go quickly through some of our test tricks. The first one is the smallest one, ETS, Easy Tribology Screener, a very useful and simple to use tribometer for reciprocating tests. And instead of talking a lot, I will show you a short video presentation of this instrument.
Congratulations. By watching this video, you seem to appreciate the importance and the cost-saving potential of tribological measurements. By taking advantage of our new technologies to reduce friction and wear, you are willing to improve your business. Fast, precise, and cost-efficient. We believe in perfect engineering, and we believe that knowledge is power. We believe in flexibility in order to innovate and to grow. Having agile and fast ways to measure and gain knowledge is paramount to succeed. We believe in preventive maintenance in order to act sustainable and cost efficient. We believe in success by being able to adapt and not by being the strongest. Don't get us wrong. Technological strength is what we essentially deliver. We believe that a product has to be simple. We don't believe in barriers. We believe that tribological measurements should be for everyone. That is why we invented the Easy Tribology Screener. We are optimal instruments because knowledge is power. Contact us to arrange a consultation and join the circle of tribology professionals.
Yes, to give you a short overview about the parameters of this tabletop tribometer, you see it's tailor-made for fretting tests with low to medium loads, very small stroke lengths, and frequencies exactly in the range usable for fretting tests. Temperature is variable from room temperature up to 200 centigrades. And the big advantage is that you also have in situ wear measurement, where we measure the wear in terms of length during the test. The other very famous and very familiar instrument to the industry is the SRV with many standard methods. And don't worry, today I won't talk about all the test methodologies and methods and standards that we provide for the SRV, but I want to point out 3 small case studies. The first case study is the fretting tests according to ASTM D7594, which is now also in the NLGI spec for high performance multi-use greases. And here I also have a small video tutorial how easy and simple it is to run SRV tests. So first you install the samples. For all the standard methods, you need ball on disk geometry, which is very cost efficient and allows you to do a lot of different parameters. The procedures are already preset and pre-programmed in the software. You just start them by pushing one button, and then the test runs fully automatically. Data is recorded and in situ visible. After running the test, you can process all the data within our software. You can export the data, hand them over to other calculation softwares. And of course, at the end of the test, you do the microscopy of the wear scars to measure the wear depth, wear volume, and wear scar diameter according to the standard method. You can also increase the throughput in your lab and save on operators' time by doing the tests automatically with our APOS option, we enable our customers to run up to 16 tests fully automatically. The second short example I want to show you are tests targeting on gear components, where we developed a quite simple but very transferable test procedure for gear fluids and gear materials on a model base, where we can easily discriminate the different scuffing performances of materials and fluids. The third interesting case study, because we have a lot of demand from the market today, is targeting on EDFs, electric drive fluids, and especially here we developed a method to dynamically test the compatibility of the stator wire with the EDF, and by adding electrical resistance measurement, we can easily see at which point we have the breakthrough of the isolating coating. You see easily how different the damage mechanisms look like after the tests. One other very interesting development that we did and are recently installing it at 2 research institutes is a hydrogen test cell up to 100 bar gas pressure. The volume of the gas is so small that there's no risk of explosions, and it allows you to run standard test methods under hydrogen atmospheres. The third test rig that we have at Optimal Instruments is the 2-disc rig, where we are doing slip rolling tests, basically targeting on fatigue mechanisms, but also abrasive wear, of course, under dynamic slip roll ratios is possible. Results look like that. You have the online recording of COF values and other interesting data like acoustic emission, electrical contact resistance, and so on. You have varying sliding speeds, varying slip roll ratios, varying contact pressures, and then you can easily do test matrices with different materials, different lubricants, different coatings, whatever is interesting to for your research. With this, I'm at the end of my short presentation. And so if you have any questions, please feel free to contact us at Optimal Instruments. Visit our website. There's a great contact form, or you can also appoint short video calls if you have questions about how to solve your specific testing demand. Thank you very much.
Thank you very much, Gregor. Very good to see all the robust options that are offered by Optimal. So now let's excuse me, sorry, come back on stage, please, as well as David. Let's now address any audience questions. We have one already from Robert for David once he comes back on stage. But before we excellent, thank you. Before we get our Q&A, let's let me just release the attendance certificate link. So that will now be available in the bottom left of your screen. So you can go ahead and click on that. You can then fill in your info and automatically generate your attendance certificate. But please don't go away. We're not stopping just yet. We have our Q&A to go. Okay, so let's begin with this question from Robert, who asks, David, would your approach address only the deformation of asperities? What about debris from excuse me?
That's a really interesting question. I mean, let me first start by saying that a lot of my interest has been where contacts are in partial slip, so that there's perhaps a proportion of the contact that's stuck, and then other portions undergo reciprocal slip. So you might get this in typical components which are in contact but are not supposed to move macroscopically with respect to each other, so like the blade roots, or could be under a bolt head or something like that. What we find in those is that the wear rates are relatively small, and actually you can pretty much assume that the contact doesn't have a great deal in the way of wear particles there. So we haven't explicitly looked at modeling wear particles, but I have, in conjunction with Chris Smith at Exeter and one or two of his research students, looked at fretting wear, and there you get some very, very interesting stuff, particularly about the generation. And in fretting you get this competition between generation of wear particles, but also how quickly they can escape from the contact. So it's quite different from, say, rolling contact wear, and you get a big difference in wear rate between the cases where the contact is just sliding backwards and forwards by a little bit, and where it's actually sliding so much that it's exposing, if you like, the wear particles, and then coming back in and perhaps brushing them out the way. So I mean, I think in principle we could do it, but we need to know something about the distribution of wear particles. I'm not sure that fundamentally it would change the overall behavior with load, but what it would do was it would introduce quite significant additional compliance, I think, probably. Yes. Yeah.
Okay, thanks.
Does that help?
Thanks, Dave. I think sounds like what it. Great.
So I think the answer is it's a long no, but or yes or something. Yes and no, I think. Yeah.
Yes, as quite funny when you were saying about the Pauli quote, when you were initially giving your introduction, that popped to mind for me as well, and I was thinking, yes, this is very much what, you know, with every scenario like that, like deformation of asperities, debris generation, it just becomes increasingly complex. And
it's a very complex problem, but of course, you know, we have some complex models, and also we have some quite powerful computers these days, and so in principle I think we ought to make a bit more progress than we have. I mean, you know, in some ways the concept of a coefficient, well, we know that the concept of what we call Coulomb friction actually was thought of by Amonton. Ken Johnson used to think of it as Amonton's friction. And actually, if you look at Leonardo da Vinci's notebooks, I haven't seen the originals, but I've seen prints of them. It's pretty clear that da Vinci knew that all about basically that frictional force depended on normal load, and was independent of apparent area of contact. And I think that's remarkable, because that's 500 years ago, and that was before Newton defined what a force was. So, you know, quite, and in some ways we haven't moved much further forward. Robert's asked another question now. Are we looking at identical materials in contact, or a different hard soft contact? Well, I think I don't like to use the word hard and soft, because hard and soft to me implies plasticity. So I think, but if you mean compliant and if you like sort of stiff and compliant materials, then there's no reason why you couldn't deal with that. In fact, the technique involves putting all the compliance on. You put all the compliance and all the roughness onto one of the bodies, and that simplifies the mathematics, but it's actually identical to having a situation where you've got yeah. So that's it. I mean, it doesn't matter. Yes, you can deal with stiff and compliant materials. Right, thank you. That's that one.
Yeah.
And then Ian says,
Question
can
from
stiffness?
Ian.
Yeah,
Yes.
Ian says, can stiffness changes during component lifetime impact stick slip behavior? Yeah, absolutely. Because if you I mean, all problems they're either if you think of running an experiment, we either run an experiment under force control or under displacement control, and there are good reasons for doing one or the other. But in general, what we do is we in a sort of actual situation, there's an element of each. So that a situation might be partly force controlled, partly stiffness controlled. Well, let's suppose it's partly displacement controlled. Let's suppose it's force controlled. Then if you change the compliance, and the contact may be the most significant thing there, then that will change the relative displacement of the two components. And if you change, if it's displacement controlled, then you change the compliance, you change the force. So yeah, there's quite a bit of influence that the stiffness can have on what's going on at the contact, and therefore on the stick slip behavior. And so if the roughness is very, very compliant, then you might get all of the relative tangential motion accommodated by deformation of the asperities, and then there's no reason for any slip at all. On the other hand, if the asperities layer is very, very stiff, then yeah, you'll get stick slip behavior, partial slip, or potentially even sliding.
Okay, thank you. That makes me think of, in terms of tribological context, have you ever looked at any modeling where you've actually looked at where the two surfaces themselves have changed mechanical properties, as in a tribologically transformed structure?
Yeah, I mean, this goes back to well, I mean, Maurice Godet down in at Insert Lyon, he did a lot of stuff on well, on third bodies, but also on tribologically transformed structures. And sadly, Maurice died relatively young, but still in contact with Marie Christine Baetto, who was his research student at the time. I mean, I think, yeah, that's another good point. I haven't really addressed it. And the interesting thing about the models that we have is that they are independent of, I mean, they're purely elastic models, so the plastic properties don't come into it, but they're independent of elastic constants. And at the first sight, that seems very strange, because you might think, well, surely if the material is stiffer, we would expect these asperities, which after all are made of that material, to be stiffer. But what you find is that if a material is stiffer, then the asperities don't deform as much, and therefore there's less area in contact. So although the material itself is stiffer, the asperities that are in contact are more highly loaded, and the effect on overall compliance is not there at all. So yeah, there you go. Oh, that's a good one from Charles.
Sorry,
yes.
would you like to read that out, or shall I, just for
yeah, you read it out. Yeah.
Okay, so there we go. A bit of a general question from Charles. It seems as though there's great interest now in applying finite element modeling to contact problems. However, I'm still amazed how much can be achieved by looking at Johnson's contact mechanics, primarily analytical models. Is there a danger that by looking too much at FE-based models, we miss out on what can be achieved analytically through other numerical approaches? Think about your modeling friction grand goal.
Yeah. I think the answer to that is yes, really. I mean, I'm a great fan of I mean, you've got two things that you can do with a contact problem. One is you can try and get an approximate solution to the real problem, and that is, if you like, well, that's what you do with finite elements, because almost always your model is not sufficiently refined to be able to capture in great detail what's going on in the contact. And the other is you can get an exact solution to an approximate problem. So you can say, well, I've got this contact problem. Which are the ones in Ken's book, or you know, more recently Jim Barber's book, or David Hill's book, or whatever it is? Which of those is it closest to? And what does that teach me about the behaviour that I expect? And certainly David Hills and I do a sort of short 2-day contact mechanics course, and we spend the first day pretty much entirely doing trying to get people to understand, you know, the if you like, the theoretical models, the analytical models, and what the consequences are for contact behaviour, because they provide such good sort of grounding in what you might expect. It's so easy in finite elements to spend a lot of time and computational effort getting the wrong answer, and not having any understanding of how to you know, of how to recognize that. So yeah, I think there's a lot that can be done with analytical solutions, and we shouldn't throw them away. You know, I mean, for a start, so many times I've seen people model an elastic contact with a sharp corner, because the CAD geometry knows nothing other than sharp corner. So they've got an elastic contact with a sharp corner, and they say this is the highest stress in the problem. And you say, well, did you do any convergence studies? Well, no, but we've got quite a fine element, so we didn't think there was a need. Do you know that this situation gives you a singularity, like at the tip of a crack? You wouldn't say that the tip of a crack gives you a stress of such and such. You wouldn't in a million years. And it's because people haven't done the groundwork in understanding contact behavior. So yeah, you know, in that situation, if you want a sensible answer, you've either got to put a radius on the corner, or you've got to put some plasticity in. But there you go. Yeah. So no, really good question, and thanks for bringing it up, Charles. Yeah.
That's a very good point. I guess part of it comes to whatever modeling approaches are almost in vogue at the time, and whatever it is that people want to tackle as well.
Yeah, I mean, you know, I think progress is it. You know, different models are appropriate for different length scales. So if you think about contacts, well, at one level you've got molecular dynamics kind of models, and that's fine down at the sort of atomic scale, but you can't build anything of any appreciable either length in time or spatial dimension before you run into computational problems. And then at the other end of the scale, you've got, you know, finite element models of complete components, and that's fine. They're absolutely perfect for doing that kind of thing. But somewhere in the middle, when we want to understand asperity behavior, well, you've got two choices. You can either absolutely characterize a certain bit of the surface and then run a finite element model on it, or you can try and do something with analytical models, as we've done here. I mean, the problem with characterizing the surface is that people tend to characterize the surface geometry. Fine, we know how to do that, and then they apply you know, isotropic bulk material properties to it, and there is no way that on that kind of length scale that you're likely to get isotropic elasticity or indeed isotropic plasticity. So you know, you've got to think of the length scales that you're trying to model.
Yes, no, the length. I was going to ask about any sort of length scale effects, and yeah, I think that kind of captures the response quite well. Seems we have no more questions from the chat, but I thought we might sort of bring Gregor in for just sort of one final question, just to kind of ask, in terms of linking up some of these great modeling approaches with the experimental results you can generate from things like the optimal platforms. What sort of, I guess this is almost a question for the both of you. David, what would you like to see from an experimental platform to help feed into your models? And then, Gregor, how can you help support some of these modeling approaches?
Yeah, that's a good one. I really liked your small tribometer. Actually, I think that's you know, that sort of thing's a lovely piece of kit, because you can do all sorts of interesting things there, in, you know, a controlled atmosphere to some extent, a controlled controlled temperature, relatively standardized conditions. You can get nice results from it, and you know, you always need nice results to validate your models. And when you you know, I mean, we have pieces of machinery that do something rather similar to that tribology tribometer. We build them ourselves for different reasons, but nice to have kind of standardized results on different materials and so on. I think that's you know, that's really helpful and really interesting. So no, I quite like the use of you know, really well designed experiments for characterizing reciprocating contact. I don't know if Gregor wants to say something.
Yes, thank you. Indeed, I think from our point of view, the interface between experiment and software is the biggest challenge and biggest demand, so that we as a manufacturer of tribometers, we are challenged today to provide data in a software readable format, so that one doesn't have to compute by his own on the PC or so that but in a way that the data, the result data, but not only the result data, also the parameters and also the machine data itself, which machine, what kind of test setup, what kind of filtering and so on, should be provided in a standardized format, so that state-of-the-art software solutions can easily handle this kind of data. And this is one of the most interesting challenges today, to find out a data format that is like common sense in the tribology society, I would say. And of course, on the other hand side, the application-oriented test parameters. Today, as you already said, David, today also the demand of testing under different atmospheres, different temperatures, different speeds is growing and growing, identifying the properties of different material combinations. Today, especially, somebody mentioned in the question, soft materials, soft in terms of plastic materials is a big topic, especially looking at, on the one hand side, 3D printed materials, on the other hand side, PFAS, the PFAS problem in the REACH field. So fluor has to be replaced as a compound of plastic materials, which also increases the demand of quick and standardized tests. And those are the topics that we are facing today, and that excite us, and that makes life interesting for equipment makers like us.
Yeah, I think that the whole issue of soft solids is a very, very interesting one. I mean, I've got colleagues at Imperial who research soft solids, you know, and they're trying to find out the properties of chocolate. And it turns out that how satisfying you find a bar of chocolate depends, yes, on its taste, but it also depends a lot on its tribological properties. And you know, I've got another colleague who's working with food manufacturers who are, if you like, trying to come up with plant-based meat. And one of the problems with your plant-based burger is you can put things in to make it taste a bit like meat, but it doesn't actually behave tribologically like meat. And so when you chew it, you don't get the same experience. And you know, for sort of people like myself who quite like a steak, it's a bit disappointing when you get the plant-based version. So I'm looking forward to them making a bit of progress on that, so I can reduce my environmental footprint.
Yes. Oh, very interesting area indeed. So I think we're now just, well, a little over our stated time of an hour. So I think now is a good point to bring the webinar to a close. So I'd just like to say thank you very much, Gregor and Optimal Instruments, for supporting this webinar. Thank you very much, David, for your fascinating presentation. Thank you both for the great discussion and great answers to those questions. Thank you very much to the audience as well for providing said questions and for being with us today.
Thank you very much for hosting the webinar today.
Yes,
great,
great
done as usually, and thank you, David. I really learned a lot today.
Fantastic, thank you both. So just a few short little reminders from me. Of course, you can find more about Surface Ventures on our website. You can, of course, subscribe to our newsletter there. Our next keynote will be on the 28th of March. More information to follow on that. We have Professor Robert Taylor from the University of Central Lancashire talking about mixed and boundary lubrication. As I said, Surface is available. You can subscribe to that via our mailing list. You can also get it on LinkedIn. And finally, for everyone, I'd just like to say, please do take the time to advertise these lectures and other content to your contacts. We hope to keep growing by getting more and more people involved. So for now, thank you very much, and we'll see you at the next keynote. Thank you all.